Hi guys, welcome back to this channel. Nice to see everyone and I hope you have subscribed to my channel. If not, hit the subscribe button now. And for today's video, we'll talk about something very important in introduction of organic chemistry, which we will talk about isomerism. Okay, we have a few learning objectives over here, but the main thing that we are going to learn today is we are going to talk about chain isomer. We are going to talk about positional isomer, and also we are going to talk about functional group isomer. We are going to learn the difference between them, and most important, we are going to learn how to draw the chain isomer, positional isomer, and functional group isomer. So, what is actually isomers? Isomers are compounds with the same molecular formula but different structural formula. What is actually this sentence means? What do we mean by same molecular formula? Same molecular formula means that you are going to have the same number of atom. Same number of atom over here means that if your compound having a C5H10O2, then the compound will have the same number of carbon, hydrogen, and oxygen. It won't change. But what is meant by different structural formula? Different structural formula over here means the arrangement are different. What do we mean by the arrangement are different? 5 carbon. 5 carbon can be arranged in many ways. 5 carbon can be a 5 carbon straight chain like this, or 5 carbon can be a 5 carbon with 1 branch. See that? The main thing over here is same molecular formula but different structural formula. The same number of atom of each and every type of atom will remain the same, but only the arrangement are different. That are isomers. There is no reaction. Bear that in mind, there is no reaction. That's why the number of carbon, hydrogen, oxygen, or any atom in your molecule shall never change. That are isomers. So, we have 3 types of isomers that we are going to learn in this video. The first one is your chain isomer. Chain isomer will be mainly differ in carbon chain. The longest parent chain will be changing. Alright, your parent chain will be different. Next, we have positional isomer. In positional isomer, obviously the name position. So the position of the branches or the functional group will change along the way. Don't worry, we'll learn in detail for each and every one of them. And the last but not least, we have functional group isomer. Obviously, functional group. What are they going to different in? Only one. They are going to have a different homologous series, or they are going to have a different functional group. We are going to look into detail each and every one of them. So, first and foremost, let's look into chain isomer. What is meant by chain isomer? Like the name says, chain means you are focused on the carbon chain. The things that will be different is the length of the parent carbon. Alright, the length of the parent carbon will be changing. Means you can have a 5 carbon straight chain, move to a 4 carbon straight chain, move to a 3 carbon straight chain. So the longest carbon chain, the longest parent chain is the one that need to be different. But the functional group must remain the same. The functional group or the homologous series should remain the same. Bear that in mind. For every single isomer, we only change one thing. There should be only one difference. And for chain isomer, the difference that we are looking for is the length of the parent carbon. Okay, let's look at some example. I have C4H9OH over here. This is the example of your alcohol. So a very standard C4H9OH will be a 4 carbon straight chain. Okay, and let's say I put my OH on the first carbon. So I complete the structure with the rest of the hydrogen. I have put down the 4 carbon. I have put down the OH. So I have 9 hydrogen left. So the 9 hydrogen will be 1, 2. Bear that in mind, every carbon must have 4 bonds. So to complete all the 4 bonds, you will eventually use up all your hydrogen. If you have extra or if you don't have enough, then you are drawing it wrongly. When the question says it's a C4H9OH, you shall never add or remove any of the atom. The structure must have C4H9OH. This is my first structure. How to make it having a chain isomer? The chain isomer means that the carbon chain must be different. My carbon chain right now is a 4 carbon straight chain. That is my carbon chain. I need to make this longest carbon chain different. So I can change it or I can make it shorter from 4 carbon to 3 carbon straight chain. 1, 2, 3. So I have 3 carbon straight chain right now, but I'm having 4. And I mentioned just now, we cannot remove or we cannot add in extra. So there's still 1 more carbon put as a branch. So when I say I put at a branch, I cannot put on the side carbon, because if I put it on the side carbon, then it will back to the longest carbon chain. Okay, so the carbon branch must be in between carbon. So this is my carbon in between. So I put in another carbon over here. So I have 4 carbon done. I put in my OH since it's a chain isomer. Alright. So your position of the OH shall remain the same. Don't change everything at one time. You only change one thing at one time. And in chain isomer, the only thing that we are changing, the only thing that should different is the longest carbon. Okay? So the OH remain on the same carbon. Sit there quietly. Okay? And then next, I have 9 hydrogen, guys. I have 9 hydrogen. Put in all your hydrogen and make sure each carbon have 4 bonds. So over here, that is your CH3. Put in the hydrogen. This carbon will another CH3. So you realize that you will have 9 hydrogen fitted in. 1, 2, 3, 6, 9. See that? So the number of carbon, hydrogen and OH remain the same. But what are changing? Look at the longest carbon chain. Look at your longest carbon parent. Your longest carbon parent changing from 4 carbon over here. Alright, changing from 4 carbon to 3 carbon. That is your chain isomer. Okay? Make sense? Alright, they are still holding the same functional group. The functional group remain unchanged. The position of the functional group also the same on the first carbon. The only thing that need to change, only one, the longest parent carbon. Okay? Simple. That is chain isomer. And as I mentioned just now, isomer means something need to different. So to be able to see the differences, you need to have at least 2 structure. When I say the longest carbon chain need to be shorter or longer, need to change, need to have difference, then you need to have one person compared to another person. That's why isomer always come in a pair, because you need to have comparison. So we always say a pair of isomers. Okay, so over here, that is a pair of my chain isomer. Okay, simple, easy. Next, we are going into positional isomer. Positional isomer. What is meant by position? Position is the one that need to change. Alright, the functional group or the substituent over here can be branches. Alright, group at a different position. Alright, so everything remain the same, but only one thing. The OH just now need to change from carbon number 1 to carbon number 2. That is what we mean by positional isomer. Bear that in mind, in positional isomer, only functional group or the branches or substituent need to change. The rest should remain the same. In the other words, you should have the same functional group and homologous series. And to make your life easier, you should also have the same length of carbon chain as parent. Okay? There is only one thing changing at one time. Don't change everything at one time. That makes your life hard. So to make your life easier, we go step by step. For every type of question, we only change one thing. And for positional isomer, we only change the position of the group. So I'm still using the same C4H9OH. So I still start with the easiest one, where I will arrange the 4 carbon in the form of straight chain. And like I draw just now, I put in the OH on the first carbon. So we still put the OH on the first carbon. Okay? And then I complete all the hydrogen. I have 9 hydrogen to go. So I have put down 2 more for the center carbon, 2 more for another center carbon, and last but not least, 3 for the last carbon. And you'll realize that the 9 hydrogen put in. Done. Okay? And for this structure, I will count this as carbon number 1, this as carbon number 2, this as carbon number 3, this at carbon number 4. So for positional isomer, we will actually focus on the position of this OH. This OH right now is located on the first carbon. So to make it as a positional isomer, your functional group need to be at different position. But the length of the carbon chain should remain the same. In the other words, to compare or to have the pair of positional isomer, the longest carbon chain remain the same, 4 carbon. What is changing, guys? The OH. The OH moving from the first carbon to the second carbon. Just simply put it down. See that? Positional isomer. Position of the functional group is now changing, making this having the same molecular formula. The number of carbon, hydrogen, OH is the same, but the arrangement are different. That is isomer. And to be exact, that is positional isomer. Complete the hydrogen. Kind reminder, every carbon must have 4 bonds. Alright, every carbon must have 4 bonds. That is your second structure. Let's look at the arrangement. So I still have the arrangement of carbon like this. Alright, do not need to number this. I'm just showing it so that you can see clearly the OH is located at which carbon. So your OH right now is located on the second carbon. So positional isomer. The functional group or the branches are changing position, but the rest of the thing remain the same. Simple. So this pairs of structure, this pairs of isomer is actually your positional isomer. Every time when you answer a question of isomer, make sure you label what type of isomer you are drawing. Make sure you indicate they are what isomer. So right now, I'm having positional isomer, so I will just simply label like that. Okay? Make sure you label that. Next, let's look at functional group isomer. So, if the chain isomer is changing the parent carbon, and the positional isomer is changing the position of the functional group or the branches. So what do you think functional group isomer is changing? Obviously, it's the different functional group. Obviously, we are changing the functional group or homologous series. And the other requirement will be the same length of carbon chain as parent. So, like the position, when you're changing the functional group, you don't change the rest of the thing. Alright? You only change functional group. But the longest carbon chain should remain the same. Okay? Don't be greedy. You only change one thing at one time. Always remember that. We have 4 different groups for functional group isomer. The first group is your alcohol and ether. Why alcohol and ether are a pair of functional group isomer? Because they share the same general formula. General formula of alcohol and ether is CnH2n plus 2O. That is the general formula of alcohol and ether. Next, we have carboxylic acid and ester. Same thing. Why carboxylic acid and ester will be a pair of functional group isomer? Same reason, because they're sharing the same general formula. That's why they will have the same molecular formula. The number of atoms in carboxylic acid and ester can be the same, but the arrangement are different. Carboxylic and ester, the general formula is CnH2nO2. That is the general formula of carboxylic acid and ester. Next, we have alkene and cycloalkane. Read carefully. Alkene and cycloalkane. And they are sharing the same general formula of CnH2n, of alkene and cycloalkane. Last but not least, the pair of functional isomer is aldehyde and ketone. And their general formula is CnH2nO1. Okay? So don't worry, we'll look into every single pair and I'll show you how they become functional group isomers. Let's start with alcohol and ether. So alcohol, we know that is holding OH. And ether, we know that is holding COC. Okay? And from just now, we know that they're sharing the same general formula of CnH2n plus 2O. Okay? So that is for alcohol and ether. And how can they become functional group isomer? Let's see. The example that I have over here, CnH2nO. Can you see that? CnH2n plus 2O. So, first and foremost, let's draw alcohol. 4 carbon, simple, we make it straight chain. So, I will have a straight chain 4 carbon. And then, I have alcohol. So, in alcohol, I need to have OH. So, let me put down OH on the first carbon. So, in this case, you have done with the C4. Alright, 4 carbon is down, 1 oxygen is down, 1 hydrogen is down. So, you have 9 more hydrogen to go. So, let's put all the 9 hydrogen into each and every carbon and make sure each and every carbon have 4 bonds. Okay, that is how we make sure your structure is correct. Make sure you calculate 1, 2, 3, 4 correctly. I mean, if you cannot calculate 1, 2, 3, 4, I'll send you back to kindergarten. Alright? So make sure you have that correctly. 9 hydrogen and each carbon with a complete 4 bond. And that is for alcohol. You're done for alcohol. And since it's an isomer, isomer means that they must come in a pair. And the pair right now must have a different functional group so that they can be functional group isomer. So, the friend or the pair of alcohol is ether, COC. And in this COC, we have used 2 carbon and we have used the oxygen. So there's 2 more carbon. So where should I put the 2 carbon? Just simply put it down. Okay? It can be on the left, it can be on the right, it doesn't matter. Okay? So the 4 carbon is down. I have 10 hydrogen to go over here. So same thing, make sure each and every carbon must have enough 4 bonds. Oxygen, most of the time, will be only holding 2 bonds. So oxygen has enough over here. Make sure the rest of the carbon is having 4 bonds. And that is your 10 hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Complete. See that? And what is changing over here, guys? The functional group. OH on the first isomer, COC on the second structure. See that? So between them, they will be called as functional group isomer. Okay? As I said previously, make sure you label them because we have many types of isomer. And this one right now is your functional group isomer. And they are isomer to each other because the number of carbon is the same, the number of hydrogen is the same, the number of oxygen is the same. Same molecular formula, but different arrangement, different structural formula. Functional group isomer. And as I promised, the same length of carbon chain. So if you look at it, the parent chain of carbon remain the same. You have 4 carbon over here. You have 4 carbon as well over here. Okay? Bear that in mind, we only change one thing at one time. Okay? Next, we have carboxylic acid and ester. So carboxylic acid, we know that is your COOH, or you can write it in the form of C double bond OOH. Ester is your COC. In the other words, is actually your C double bond OOC. That is your ester. Okay? And they are functional group isomers, same reason, because they are sharing the same general formula. So the example that I give to you over here, CnH8O2, that is your CnH2nO2. Both carboxylic acid and ester will have the same general formula. So let's start with carboxylic acid. Carboxylic acid over here is your COOH, C double bond O, OH. Okay, so I have 4 carbon, guys, but I have used up 1. So I have used 1. Oxygen 2, settled. Hydrogen 1, I have used 1 hydrogen. So I have 3 carbon left over here. I just simply put it in the form of straight chain. Simple. Okay, so carbon done. All 4 carbon is done. Hydrogen, you have 7 more. So let's see where the 7 should go in. Simple. Make sure your carbon having 4 bonds. Then your hydrogen should be just nice. Bear that in mind, you cannot add or you cannot remove any of the atoms that have given to you. That is my C4H8O2 for carboxylic acid. Okay? And we should go for ester right now. Ester must have C double bond OOC. So draw that first. I must hold C double bond O. I must hold single bond O bonded to a carbon. Over here, having a bond. And as you can see, we have used 2 carbon, guys. We have used 2 carbon over here. So minus 2 carbon. Oxygen done. 2 oxygen done. So I have 2 more carbon. Alright, let's say I put in 1 at the left, 1 at the right. No problem. It can be both on the left, it can be both on the right. Doesn't matter. Okay? And then you are done with the carbon. So I have 8 hydrogen left. I have 8 hydrogen left. Make sure all the hydrogen are put into the correct place. Alright? And make sure you check who is actually holding the hydrogen. Each and every oxygen can have only 2 bonds. So the oxygen is already done. The hydrogen should go only into carbon. And from here, you can see that we are changing from the functional group of carboxylic acid in the first structure, changing into carboalkoxy ester in the second structure. So these 2 will be the functional group isomer. Simple. Next, we have alkene and also cycloalkane. Alkene, obviously, CnH2n, and very obvious, carbon double bond carbon. While cycloalkane must have a ring. Doesn't matter how many carbon, but you must have a ring and only carbon single bond. And the general formula that they are sharing will be CnH2n. As you can see, I have C4H8. The simplest alkene that I can have is a 4 carbon straight chain with 1 double bond. Let's say I put the double bond on the first carbon. Complete the rest of the hydrogen. The 4 carbon is completed. So I have 8 hydrogen to go. Make sure you count 1, 2, 3, 4 correctly. So this carbon can only hold 2 more hydrogen due to the presence of double bond. So 4 bond complete. This carbon, the second carbon, can only hold 1 more hydrogen. 4 bond complete. So can you count 1, 2, 3, 4? Make sure you can do that well. Don't miscount 1, 2, 3, 4. No one should wrong in counting 1, 2, 3, 4. Okay? So C4H8. 4 carbon, 8 hydrogen complete. And that is your alkene. How about cycloalkane? Cycloalkane means a carbon-carbon single bond ring. So 4 carbon ring should look something like this. Your skeletal. 4 carbon over here, that is your carbon 1, carbon 2, carbon 3, carbon 4. And it's a skeletal structure over here. If you didn't put in the hydrogen, this is also correct. But just to show you where is the hydrogen is actually bonded to the carbon. Every carbon over here will hold 2 hydrogen to ensure the carbon having 4 bonds. This hydrogen is not necessary to show because your ring is in the form of skeletal. Alright, if you don't remember what is skeletal, go and check on the video 1.2. And this 2 is what we call functional group isomer. And this functional group isomer is a pair of isomer between alkene and also cycloalkane. Simple? Very simple. Because you are changing from carbon-carbon double bond to a cyclic carbon-carbon single bond. Okay? That is functional group isomer. Changing the functional group or changing the homologous series. Simple. Next, we have aldehyde and ketone. What makes aldehyde and ketone special is both of them holding C double bond O. But what makes them different is the C double bond O in aldehyde must be holding next to a hydrogen. While for ketone, the C double bond O must be sitting in between the carbon. That is the reason why they are sharing the same general formula, CnH2nO. So let's start with aldehyde. Aldehyde must have a C double bond OH. So I will start with a C double bond OH over here. C double bond OH. And in this aldehyde, I have used 1 carbon. I have settled the oxygen and I have used 1 hydrogen. I have 3 more carbon left, guys. So the only place that we can put the 3 carbon is on the right. 3 carbon. Because on the left is already full with hydrogen. Okay? Settle with the carbon, put in the 8 hydrogen. Same thing, make sure each carbon contains 4 bonds. And that is my C4H8O. If you don't trust me, you can count the number of carbon, hydrogen, and oxygen. Settle with the aldehyde, go for the ketone. So how should a ketone look like? We always start with what we want. We want a C double bond O, CC. So I start with C double bond O is a ketone, CC. And from what I want, I already used 3 carbon. Guys, I already used 3 carbon and 1 oxygen settled. I have 1 more carbon left. You can put it on the left, you can put it on the right. 1 more carbon left. So carbon settled. Hydrogen 8, make sure you count very carefully who is holding the hydrogen. Make sure the hydrogen that you put in is at the correct carbon and every carbon can only hold 4 bonds. See that? What is changing? Aldehyde and ketone. Ketone is located between carbon. Okay? Aldehyde must be as the last carbon holding to a hydrogen. And this is the last functional group isomer pair that we are going to talk about. Simple, easy. Just one kind reminder. Don't be greedy. Change only one thing at one time. So, a bit of conclusion for today. Your isomers must come in a pair. At least a pair. So, you must have a structure A and a structure B. Then only you can compare. The position is changing. The functional group is changing. Or even the longest carbon chain is changing. Okay? If I only have one thing, how do you compare? How do you know that the position is changing? If you only have one thing, how do you know that the functional group is changing? So to know something is changing, something is different, you need to have 2 things. 2 structure that have the same molecular formula means the 2 structure must have the same number of atoms. Okay? Next, the isomer can only change one thing at one time. If we are talking about functional group isomer, you only change functional group. the longest carbon chain, the position remain the same. If you are talking about positional isomer, you only change position. The functional group is the same, the parent chain also the same. Isomer must have the label because we have three types of isomer. You have chain isomer, you have positional isomer, you have functional group isomer. So when you say they are isomers, make sure you label what isomers you are talking about. Okay? Simple, easy. And that is everything about isomers. Next, let's try to do some exercise. I give you two types of question over here. So if you encounter different type of question, okay, you can always ask me in the comment below. So, show the chain isomer, positional isomer, and functional group isomer for the molecular formula C5H10O2. C5H10O2 is obviously your COOH and also your COC. Okay? For this type of question, you do not need to draw everything. You only need to draw a pair for chain isomer, a pair for positional isomer, and a pair for functional group isomer. And like I always say, make sure you label them. So if I'm drawing for chain isomer, make sure you label this is chain isomer. So the chain isomer, I'm changing the longest carbon chain. Let's start with the 5 carbon straight chain. 5 carbon straight. I start with the carboxylic acid, COOH. So I put down C double bond O, OH. I have 10 hydrogen. I have used 1. I have 10 hydrogen. I have used 1. I have 9 more. So the 9 will be into each and every carbon to achieve 4 bonds. That is only the first structure. Bear that in mind, isomers must always come in a pair, so I need to find the front to show that the chain isomer is changing. The longest carbon is changing. So from 5 carbon, I'm changing it to 4. So 1 more, we need to put it as a branch over here. See that? Chain isomer means the longest carbon chain is different. It would remain the functional group. The functional group and the position of functional group should remain the same. We're only changing one thing at one time. Only make one thing different at one time. So put in all the hydrogen at the correct position. Make sure, count carefully on the 1, 2, 3, 4. So both of this must have C5H10O2. And that is your chain isomer. Next, I can have positional isomer. So for positional isomer, you need to change the position of the functional group. But in this case, very special case is the COOH functional group must located on the side carbon. If you look at it, C double bond O, OH is already 3 bond. Single bond OH, double bond O. So the COOH must located on the side. Okay, it must located on the side. So whose position can be changing in positional isomer? Look at this, the CH3. I have this as the first carbon, second carbon, third carbon, and fourth carbon. And in this case, the CH3 is on the third carbon. I can move the CH3 to the second carbon. And you can see we have positional isomer. Let's try. So I'm still having 4 carbon straight chain. My double bond OH is still on the first carbon. I'm copying this back. My CH3 is here. Complete all the carbon with hydrogen. Make sure you don't put extra. Make sure you check with the molecular formula that is given to you. C5H10O2. C5H10O2. Okay? And the positional isomer is changing the position of this branch. Bear that in mind, positional isomer is not only changing the position of functional group or homologous series. We can also change the position of the branch or the substituent. So the 4 carbon remain, guys. The C double bond O, OH also remain. The only thing that changing over here is the position of this CH3 moving over here. And complete the carbon with hydrogen that you have. You'll realize that both of these will still be holding C5H10O2. And the only things that is changing is this position of substituent. It's changing because this is carbon number 1, 2, 3, and 4. This is located on the third carbon, and over here is located on the second carbon. Can you see that? Alright, positional isomer. So always remember, positional isomer is not only changing the functional group, you can also change the branches, the carbon branches. Okay? Next, functional group isomer. And obviously, functional group isomer for carboxylic acid is your ester, COOC. And the first one, we always start with the 5 carbon straight chain of carboxylic acid. I have my C double bond O, OH on the first carbon, definitely. And then I have another 4 carbon to go with the complete hydrogen. And this will be your C5H10O2. Okay? So you can count it if you don't trust me. So that is your C5H10O2. And the functional group isomer, the partner of COOH, is your ester. So I can have my ester like this. Double bond O, single bond O, bonded single bond to CH2, CH2, CH3. And you can see over here, 5 carbon, 1, 2, 3, 4, 5, 10 hydrogen, 3, 5, 7, 10, with 2 oxygen, C5H10O2. Simple. So this is a type of question where the question asks you to show a pair of chain isomer, positional isomer, and functional group isomer. And that is how we label them. Okay? Another type of question is this, all possible isomer. When the question say all possible isomers, means you need to draw all the possible isomer for it. And then only you indicate the chain isomer, the positional isomer, and the functional group isomer. So let's see how are we going to answer this. It's a C4H8. So for C4H8, obviously, is the carbon-carbon double bond and also the cycloalkane. So let's start with all the possible isomer. Let's start with a C double bond C straight chain 4 carbon. The way that to draw all possible isomer, start with the simplest first, 4 carbon, double bond on the first carbon. Put in the hydrogen that you have. Label this as my Roman 1, structure number 1. The second structure is, don't mix everything up first, go for the chain isomer. Alright, you can make it shorter from 4 carbon, make it shorter to 3 carbon. So you have 1 more carbon, put it in the center. The position of double bond remain the same on the first carbon. Complete it. Alright, put down all the 8 hydrogen. Put down all the 8 hydrogen. Make sure you count 1, 2, 3, 4 very, very correctly. Okay, so that is my second structure. Label that. Okay. Next, so you have 4 carbon changing to 3 carbon. You cannot have 2 carbon because 2 carbon, then it will back to the longest carbon chain 4. Okay, so you cannot have 2 carbon longest chain. Since we are done with the chain isomer, let's move to position. So for this one, the position is changing the double bond from first carbon to second carbon. So my structure number 3 can be 4 carbon straight chain, changing the double bond from the first carbon to the second carbon. Okay, complete the hydrogen. That is how we draw all the possible isomer. Don't draw as you wish. Make sure you know every time when you are drawing, you know what are you changing. Then you won't miss any of the isomers. That is my structure number 3. Okay, label everyone. There is a use for the label, so make sure you do that. So can we still move the double bond? No, we cannot move the double bond because if we move it, it will back to the first carbon. Okay, so we are not going to move it. means that we are done for this position isomer. For this 3-carbon chain, we also cannot move the double bond because when we move it, it will also back to the first carbon. Alright, if we are moving down here, it will also back to the first carbon. So for this one, we don't have any positional isomer for this. Okay. Since we are done with chain isomer and positional isomer, next we move to functional group isomer. So for carbon-carbon double bond, the functional group isomer is cycloalkane. Cycloalkane 4-carbon. Okay, structure number 4. See that? 4-carbon. Next, other than 4-carbon ring, we can have 3-carbon ring. And the 3-carbon ring will have one more carbon as a branch. And it's still C4H8. That is my structure number 5. Okay? So we are moving from the chain isomer, this one. Between that is your chain isomer because the longest carbon chain in the ring is 4. The longest carbon chain in the ring is 3. So all the possible isomer for C4H8 is 5 of them. My Roman 1, my Roman 2, my Roman 3, Roman 4, and Roman 5. And what is the use of the label of every Roman? Simple. We are going to use this to indicate the chain isomer, positional isomer, and functional isomer. So label that chain isomer. So which structure is chain isomer to each other? So you know that Roman 1 and Roman 2 is the chain isomer to each other because the longest carbon is changing from 4 carbon to 3 carbon. So chain isomer Roman 1 and Roman 2. That is the use of the label. We only need to indicate, alright? So it's a waste of time for you to draw the isomer again. What's the best way? Label the isomer, use the label, and that's it. Okay, and you get marks for that. So make sure you label them when the question say draw all possible isomers. Next, I need to show the positional isomer. So which one between them is positional isomer to each other? So obviously, the positional isomer is the changing of the position double bond. So this one, the carbon double bond located on the first carbon. This one, the carbon double bond located on the second carbon. So the positional isomer over here is Roman 1 and Roman 3. Label them correctly. Simple. Last but not least, which between them is functional group isomer. Functional group isomer can be any of the 1, 2, 3 to Roman 4 and Roman 5. Okay, you can take Roman 1 and 4. You can take Roman 2 and 4. Or you can take Roman 1 and 5. Or so on. So any one of the 1, 2, 3 pairing with the 4 and 5 is also functional group isomer. As long as you are pairing up the carbon-carbon double bond with the cycloalkane, that is your functional group isomer. Simple. So 2 types of question that I'm showing you over here. One is to only show a pair of isomer that they're asking for. Another type of question, which is drawing all possible. Bear in mind, when you are drawing all possible isomer, don't draw as you wish. Make sure you know the flow. Draw the longest first and then moving to the chain, moving to the position, moving to the functional. Then you will be able to get all the isomers. Okay? And I hope this video helps you to understand about isomerism. And if this video helps you a bit, give me a like for this video. And don't forget to subscribe to my channel. If you have any questions, feel free to drop in the comment below. I'll see you in the next video and thank you for watching.